Welcome students. This is the fifth session in Control Systems Engineering. In the previous session, we saw root criteria. In this particular session, we will be studying root locus technique to check the stability. Let us quickly revise what we saw and what we learned in the previous session. We saw that using a transfer function characteristic equation, it is possible to determine the stability of the system. Root criteria is the technique in which we make up a root array and write down the coefficients in a particular manner to check and analyze the stability of the system. In root criteria, we saw that by solving the algebraic equation, we comment on the stability of a particular system. Let us take an example. Let us say we have characteristic equation as s cube plus 2s square plus 5s plus k, where k is a constant. Now we have to find out the range of values of k for which this particular system with characteristic equation given will be stable. Now we will form the root array. By forming the root array, we have following table. Two and k here. By solving this, we get 10 minus k by 2 and 0 here. By solving further, we get k over here. Now as you can see, according to root, the first row of the root array should have all the same signs. Now as 1 and 2 are positive, for this system to be stable, we need 10 minus k by 2 and k, these terms to be positive. Hence, we can form the condition for stability as should be greater than 0 as well as k should be greater than 0. According to this, the limiting condition that occurs is k should be greater than 0 and should be less than 10. That's why we have a range for the values of k, that is, and between 0 to 10, k will be giving such values to this particular characteristic equation such that the system will be stable. Now, as we saw here, we saw that there is a particular range of values of k, and hence, as we change this particular parameter, still the system is stable. But if we change k beyond 10 or change k so that it becomes less than 0, system will no more be stable. Now, what if we have a technique in which we are able to see graphically how the stability is moving or how particular roots of the equation are moving according to the change in parameter? What if we are able to see after what value is stability changing? This very technique is nothing but root locus method. Root locus method is a geometric method to analyze the stability of the system. It is also a qualitative method to determine the stability of the system. Not only you will be able to tell if a system is stable or not, you'll also be able to comment if which system is more stable and which system is less stable. You'll be able to see the margin, or you'll be able to see the range of values of k graphically, or range of values of different parameters that you choose. As you change them, how well or how differently the stability changes. We will see and look into this particular detail in following slides. Let us see what you are going to learn in this particular session. So initially, we will be going through the basics of root locus. We will be seeing the definitions and understanding behind the root locus technique. What exactly is a root locus that we will see. Also, we will see some of the conditions which are required for a root locus to stay valid. And as I already mentioned, root locus technique is a geometric method. So, in a particular exam, if you have a question regarding root locus, you'll be able to draw a quick root locus and see the system in a detailed manner. For that, we have root locus rules for drawing the locus. In that particular session, we will see the rules and also see how stability is associated with this particular technique. Let us go forward into the next slides and see the root locus basics, in which we are going to see the definitions and some of the typical root locus diagrams. Now, all of you already know that a particular transfer function or a closed loop transfer function is given as g of s upon 1 plus g of s h of s. Now, this particular g of s h of s is generally represented as a particular transfer function or in a particular fraction. So, if I'm looking at the characteristic equation for a closed loop system, it will look as 1 plus sum k into a of s upon b of s, or rather we can write it as 1 plus k into f of s. So basically we are going to change this k and we are going to see how the roots of this particular equation change. Because if you have a characteristic equation as 1 plus k into f of s is equal to 0, ultimately if we are going to change k, we will be able to find out different values of s for which this system is valid or this particular equation holds true. And this is exactly how we will find out many values of s for different values of k, and we are going to find out the locus of roots, and this is how we are going to draw a root locus diagram. Let us see some basics regarding the root locus technique. So, root locus is nothing but a locus of poles and zeros of a transfer function. So, we saw that for a transfer function g of s h of s, if you have k a of s and upon b of s, so roots of a of s are nothing but zeros and roots of b of s are nothing but poles of the transfer function. And this is how we are going to plot the zeros and poles for different values of k, and this is how we are going to form a locus. Also, root locus gives clear qualitative picture of how closed loop poles move around. So, in a qualitative manner, we will be able to see how poles and zeros move in S-plane. As you already know, the roots of this particular equation will give different values of s, and we have S-plane as sigma plus j omega, and we'll be able to plot different values of s and we'll be able to join them and we'll be able to form a locus. Also, root locus method is a geometric method as opposed to the algebraic roots criteria that I already described you. Also, for the basic rules, just remember in S-plane, a pole or the root of the denominator of transfer function say B of S, is represented as a cross. So whenever you have a pole in S-plane, it will be represented as a cross. And 0 is represented as a hollow dot. So you have the root of A of S as 0, which will be represented as a dot or a hollow dot like this. Remember this so that we can move forward and see different root locus diagrams in general. Typically how a root locus looks like. As you can see, there are few diagrams over here. In the red locus, you can see there are different loci. So this is the S-plane, and you can see the arrows representing the directions of this particular root locus, or say like this. Also you can see the circle. Okay. As you can note, there is something typical about these root locus. The root loci are symmetric with respect to the x or sigma axis. As you all already know that when a root of characteristic equation lies in the left hand side of the S-plane, the system is said to be stable. All these red marks that you see in the diagram represent the values of roots or the values of S. Now, as you can see graphically, you exactly know at what value of K this particular value or the red diagram crosses the j omega axis and goes into the right side of the S-plane. And this is how you know that the system will not be stable after a particular value of K when this particular diagram is crossing the j omega axis. Also you know that say if this particular pole value is -5 and for this particular pole value if this is -2, let us say for K is equal to 50 we have this value, and let us say for K is equal to 100 we have this value. This is just the example. The emphasis I am going to make is that for K is equal to 50, if you have the diagram over here, and for K equal to 100, if you have a diagram over here, you know that for K is equal to 50, system is more stable than for the value K is equal to 100, because from j omega axis, this pole is close than the value s equal to -5. More the system is away from the j omega axis, stable is the system. So the this part which you can see here is closer to j omega axis than this part, and hence when system is around this part, system is more stable, and when system is near j omega axis, system is relatively less stable. This is the total analysis that you can do with root locus diagram once you draw a root locus. So next up is the magnitude and angle conditions. These are those conditions which justify for a point to lie on a root locus. If a point, a random point, if somebody asks you if this particular point S0 lies on a root locus of a particular transfer function 1 plus k f of s, if somebody asks you that, you can check looking at this transfer function that if S0 lies on a root locus of this particular transfer function. And before solving any problem, if such questions arise, you'll be able to solve this particular question or such questions where it is necessary to check if a particular point lies on a root locus or not by magnitude and angle condition. Let us go forward and see what exactly magnitude and angle conditions say. Let us see what is magnitude and angle condition. Consider we have a particular transfer function or transfer function characteristic equation as 1 plus f of s is equal to 0. Now, values of s which satisfy this equation will form the root locus. Now, for any value s naught to satisfy this equation, it must satisfy magnitude condition. Now, what is magnitude condition? We can see by rearranging this equation. Let us assume this f of s is nothing but k upon k into a of s upon b of s. A of s is the product of the factors which form the zeros, and b of s is nothing but the product of factors which form the poles of this particular equation. So we have 1 plus k into a of s upon b of s is equal to 0. Hence, we have minus 1 is equal to k a of s upon b of s. Taking magnitude on both sides, we will have magnitude of this particular term, that is k into summation of all the magnitudes of factors of this particular a of s. Let us say this is how there are factors over there, and I is equal to 1 and now z or zj represents the different zeros of transfer function, and pi or p represents the poles of the transfer function, and this particular pi terms represent the product of such different zeros, and this particular term represents products of such different poles, and we get magnitude f of s to be is equal to 1. So for any s naught to satisfy this particular characteristic equation, it has to follow this particular magnitude condition. Okay, let us see what is the angle condition. According to angle condition for root locus, for any point s naught in the s plane, it has to satisfy that the angle that particular point makes with the zeros and poles should combine to form the angle phi, which is nothing but odd multiple of 180 degrees. Okay, so this particular s naught we have, for which we have to check if this particular s naught lies on root locus or not. And if we have some different poles, look like these, if we have a 0 here, and we have to check what angle does this particular s naught makes. Okay, if this is s naught, this is the point s naught, we will be able to check what is the angle made by s naught with these particular poles and zeros. So we have say minus a, minus b and minus c. We can see what angle is made by these 2 points. So let us join the lines. Okay, so this is another line and this is another line. We'll draw the horizontal and we'll calculate angle in the anti-clockwise direction. So you have this particular angle first. Let us say theta 1. You have theta 2. Also, you have theta 3. Now, we will do the summation of all the angles made up by zeros first and subtract the summation of angles made by poles. So what are the angles made by zeros? Which are nothing but this theta 3 first, then we'll subtract the summation of angles made by the poles, which are theta 1 and theta 2. And we will check if this particular phi is the odd multiple of 180. If this angle condition is satisfied, then we can check if this magnitude condition is also right. Okay, so initially you will have to check the angle condition, and if angle condition is checked and verified, you can then go for the magnitude condition. Okay, so let us take an example where we have 1 plus f of s is equal to, say, k upon k into s plus b upon s plus a1 and s plus b1, where plus 1. So we have f of s is equal to this particular equation. Okay, now we are going to see if the angle of f of s is the odd multiple of 180 degree for a certain point lying between a1 and b1, or minus a1 and minus b1. Let us first plot the poles and zero locations for this particular equation. Let us say we have minus b here, say we have minus a here and minus b here. Now we are going to check if our point, the required point that we are looking at, is satisfying the angle condition or not. So let us say we have s naught between a1 and b1, or say minus a1 to minus b1. Let us plot s naught here. So we have our s naught at this particular position. Now we will join s naught with every other point. Say we joined it by minus b. So from horizontal you have the angle of 180 degrees in the anti-clockwise direction. Now if you join minus a with s naught, say this way, okay, so you have with horizontal 0 degree angle, and if you join minus b with s naught, again with horizontal you have 0 degree angle with s naught. Okay, just look at the direction, because we draw the horizontal from minus b in the right hand side. Also the phasor going from minus b to s naught is also on the right hand side. The angle is 0, but just in case of minus b, the horizontal goes in the right hand direction, and the phasor from minus b to s naught, which is this point, goes in the left hand side, and hence the angle is 180 degrees. And that's why you know that the summation of angles from the poles and zeros, which is nothing but 0 degrees minus 0 plus 180, which is nothing but minus 180 degrees. Okay, which is nothing but the odd multiple of 180 degrees. And hence for the point lying between minus a and minus b, this point, the locus between minus a to minus b, will lie on the root locus of this particular function. Okay, now by checking this particular condition, that is the angle condition, we can go forward and check the magnitude condition for s naught. Let us go forward and see how to draw a root locus. So there are different rules, around 10 rules are there for the drawing of root locus. Let us see those rules one by one. And these rules are interconnected, and these rules also give us the insight of how the roots are moving in a particular S-plane. Let us go forward and see the first rule, which is symmetry. So as you know, root locus is nothing but the locus of roots, and you also know that roots occur or appear in conjugate pairs. So if you have a root s is equal to 2 plus 3j, you will also have another root 2 minus 3j, and that is why for a particular S-plane and a particular, let me use another color. So for a particular root locus in the vertical half of the S-plane is like this. Okay, if root locus is like this, the root locus is symmetric across real axis, that means this axis, and that is why you will have the exact water image of the figure above the real axis. So if you are able to draw the root locus above the real axis, it is very easy to recreate the root locus below the axis, because these are symmetrical diagrams in root locus. Okay, so you will have symmetry across this particular axis, and because these roots occur in conjugate pairs, so if root locus is true for this particular value, it will also be true for its conjugate pair, and that is why you get the symmetry. Okay, so this is a very simple rule. You can study the rest of the rules, and once you are able to draw the vertical half first, it is easy to draw the next, or the below vertical half, or the other half of the root locus. Let us see the starting and terminal points of particular root locus. Okay, as k varies from 0 to infinity in a particular transfer function, say 1 plus f of s we have. Okay, and in this particular f of s is nothing but k into some a of s upon b of s. So as k varies from 0 to infinity, locus starts from open loop poles and end at the open loop zeros, or at infinity. For n poles and m zeros, n minus m loci end at infinity. To illustrate this, I'll use some example. Let us use another color. I'll use black. So let us say we have f of s is equal to k into, let's say we have s minus, or say s plus 2, s plus 3, s plus 1, and if we have some poles as s plus 4, s plus 5, s plus 6, s plus 7. So we have three poles, we have three zeros, and we have 4 poles. Now, as according to this statement, as we vary k, locus will start from open loop poles. So there will be 4 different root loci segments. Why 4? Because we have 4 poles. For n poles, if we had n poles here, we would be having n different root loci segments. So just remember, the number of different root loci segments is nothing but the different number of poles that you have. So in this particular example, we have 4 different poles and 3 zeros. Now these 4 different root loci segments will start from the poles and will be traveling towards the zero. But as we have just 3 zeros, one of the pole does not have a zero to go. So that particular zero, that particular root loci segment will start from a pole but go towards infinity. Okay. So this is the root. So we will now see how exactly these particular root loci segments travel. But for now it is important to see how these particular root loci start and how these particular root loci end. So just for an example, I will draw this particular diagram for this root loci. So we have 3 zeros at -1, -2 and -3, and we have 4 poles at different positions. So we have -1, -2, -3, -4, -5, -6 and -7. Okay. So the root loci will somehow start at a particular pole. Let us say this pole. Okay. And thus this particular root loci will travel towards a particular zero. So this is how we will decide the direction of the root locus. As you vary k from 0 to infinity, okay, as you go from 0 to infinity, the root locus will start from a pole and end at a 0. Let us say -4 will start at -4. The root locus will start at -4 and go towards -3. Okay, so this is how a root locus will go from -4 to -3. From -5, a root locus will go as this. Okay, and go towards, let us say, this particular root locus will go towards -1 and -2. So from -6, some root locus travels through this path and goes to -1, and from -5, a root locus starts in this way, travels this way and goes this way and goes to -2, and from -7, maybe the root locus will go in this particular direction towards infinity. Okay, minus. So infinities are at different locations. All of you might be wondering, why did I draw a root locus in this specific manner? Because this is the right diagram for this particular root locus, and I will explain you how did I write this particular, or how did I draw this particular diagram itself. We will use the same example for explaining the other rules also, so that you will understand. So as you vary k from 0 to infinity, we will be getting such a diagram. Okay, just remember. So from the poles, root locus is starting and it is ending at a particular 0, and for the poles which do not find the other 0, it will go to infinity. So we have n is equal to 4 poles here, m is equal to 3 zeros, and that is why we have 4 minus 3 is equal to 1 root loci segment going towards infinity. That's what this particular statement says. Okay, we'll use the same example for the different rules. We'll go forward and see what is the other rule. So asymptotes to root loci. The m minus n root loci which tend to infinity do so along asymptotes radiating out of a single point on a real axis. Okay, so in the previous example, or in the previous rule that we saw, n minus m root loci segments travel towards infinity. Now these root loci, if there are 3 such root loci segments which are traveling towards infinity, they do so from a single point. They do not travel from different points, but they radiate out from a single point. Let it be 3, let's say 4 or 5, or say many different n minus m root loci segments traveling towards infinity. They'll be traveling along or traveling from a single point. Now that point value is given by this particular equation. Okay. So in a previous example we saw f of s is equal to k, and we had this s plus 1, s plus 2, s plus 3, and we had s plus 4, s plus 5, s plus 6 and s plus 7 as values. Okay. So now we can check, we will see the summation of a real part of the pole. We'll subtract the summation of real parts of zeros and we'll divide it by n minus n. So let us do that. It gives us minus a is equal to the real parts of poles are nothing but minus 4, minus 5, minus 6, minus 7, subtracted minus 1, minus 2 and minus 3, divided by 1, because n minus 1 is equal to 1 in this case. So we have minus 22 plus 6, okay, divided by. So we do have this particular point as minus 60. Okay. So in this particular example, the root locus, which is radiating out of minus 7 towards infinity, will travel along minus 60 towards infinity. Okay. So you have minus 7 and it will go towards infinity. Now it is important to see that the root loci which are traveling towards infinity, that we accepted and we saw that they really travel towards infinity, but at what angle or at what direction they travel so? Because in the S plane you have infinity in all directions. Okay. Just not in this direction or this direction. There is infinity at every direction, and that's why it is important to see at what angle that particular root loci segment travel towards the infinity. Now we just saw that for this particular example from minus 7 and the root loci is traveling through minus 16 towards infinity, and I drew it in the horizontal direction. Let us check if this was right. Okay, let us erase everything, and that now we had 4 poles and 3 zeros. Let us calculate the angle at which this particular root loci segment, which was only 1, will travel towards infinity. The angle would be given by 2q plus 1 upon value of n minus m, which is 1, and into 180 degrees here, and q will be 0, 1, 2 depending upon the number of root loci segment. As we just have one root loci segment, we will just put q equal to 0. Okay. So for q is equal to 0, we have angle is equal to 180 degrees. And as you can see in the diagram from minus 7, I had drawn a root loci segment going towards infinity. Okay, through minus 16, but at the angle of 180 degrees from the horizontal. Okay, so for this point minus 60, actually I marked the angle at a different or the wrong position. It should be around minus 60. So you have this point minus 60 through which we are radiating out this particular root loci segment going towards infinity. The angle it makes with the horizontal is nothing but 180. Okay, so this is how you'll be able to draw different root loci segments at different angles traveling towards infinity. Let us go forward and see on a real axis how to determine if a part is on a root locus or not. This is a very simple technique wherein we'll again mention the same example where we had three zeros and we had four poles. As if you remember, we had poles at -4, -5, -6 and -7. We had zeros at -1, -2 and -3. Okay, so let us draw poles and zeros again on this particular diagram. Okay, so we have -1, -2, -3, -4, -5, -6 and -7. Now, how to determine if which part is actually on the root locus? So, if a point on a real axis lies on the root locus, if the number of open loop poles plus open loop zeros on the real axis to the right of that point are odd. Okay, so if you are talking about this particular point here or this segment wherein you have to check if this particular part lies on root locus or not. So what you have to check is the total number of poles and zeros to the right of this particular line segment or this particular root locus. So you have this root and this root. So these are three zeros over here and 0 poles. So you have 3 plus 0, 3 poles and zeros, which is odd, and that is why this particular segment will lie on a root locus. So I will use different color to show those parts which lie on a root locus. Let us use red color to show. So we have this particular line segment or this particular loci which lies on the root locus. We'll start from this two. So on this particular, for these points on the right side you have 1, that is odd. For these you have 2, so there will be no root locus here. For this also there will be no root locus. Again for this part there will be root locus because you have 1, 2, 3, 4 and 5 poles and zeros which are odd in number. So you have this part also. And again we had this particular root loci going towards infinity from -16. So in the right hand side you have 7 poles and zeros which are odd, and that's why this part also lies on root locus. So if you remember, we had the diagram as this, which is nothing but a circle. Sorry for my drawing here, but this is how our diagram looked like. So if you remember or if you revise, I have now cleared why specifically I drew such a diagram in the first place, in the very first rule of the root locus drawing rules. When I draw such diagram, now you might understand why did I draw such a diagram. Now the only part left is this part. Why did I draw such a part? Now that you know that this part lies on root locus and this part lies on root locus, it is important that these are poles and these are zeros. It is important for root locus to travel from poles to zeros. Okay, so it is important that a root locus from this pole goes to one of the zeros here. So you have 2 poles and 2 zeros. That's why we travel out of the real axis towards these zeros. But why a circle? Okay, so this circle can be explained by the rule where we describe the angle condition. Okay, so if you have a particular transfer function and if you represent it like this, s plus j omega plus certain value of s naught And then if you have different s plus j omega plus s naught, or say s1, then you have s2 plus j omega 2 plus s naught. If you try to solve these equations, and if you apply the angle condition, and in the angle condition you will have ultimately tan inverse of a particular function to be is equal to 180 degree for angle condition to be satisfied. And if you, for that, these angles or the angle terms in this particular bracket will have to go to 0, and if you solve that, it gives the equation of a circle, and that's why you get a circle over here. Okay, so this is the explanation of a circular root locus in this particular diagram. Okay, this is, the proof is not really important. This is out of the syllabus explanation for you to understand why this is a circle. So I hope you have understood how are the basic rules of root locus segments. Let us go forward and check so how to determine the intersection of root locus with imaginary axis. Okay, so intersection of a particular root locus with imaginary axis can be found by Rao's criteria and by finding the limiting value of k. So let us consider that you have a particular f of s is equal to as follows. You have complex conjugate pair of poles also. And if you find out the characteristic equation, it looks like this, wherein s raised to 4 plus 9s cube plus 43s square plus 143 plus ks plus 204 plus 2k. If you find out the Rao's array and take out the limiting values of k, that you already know that this is plus 1 and this is this is plus 9. These values that you see here should be positive, and if you solve this equation, you get the limiting value as k is equal to 108.4. And after you get this limiting value of k, you go to the auxiliary equation, which can be shown by the s square rule, and we can put this particular equation 204 minus k upon 9 s square plus 204 plus 2k is equal to 0. And if you put the value k is equal to 108.4, you are going to get value of s is equal to plus minus j into 5.28. So this is how you will be able to find out at what particular point does a root locus intersects the imaginary axis. And as you know that at this point the root locus cuts the imaginary axis, the stability notion will change. The system is going to be unstable, and that's why this particular limiting value of k is important to know. Let us go forward and see what is the angle of departure. So angle of departure of root locus from complex open loop pole is given by phi p is equal to 180 plus 5. Now you already know that root locus segments start from the poles. At what angle do they start is important, and that is why this particular phi is given by the summation of angles from 0. So if you have a diagram of poles and zeros like follows. So if you have a pole here and a conjugate pair here, and if you have a 0 here, pole here and a pole here. So you have 4 poles and 1 0. Ultimately, for this particular segment, you have in total 3 poles and zeros on the right hand side. So this will lie on root locus, and hence this root locus is going from pole to 0. This particular pole lying on real axis, it will travel towards infinity in this direction. The centroid, or the point from which the asymptotes of the poles traveling towards infinity when they originate, is somewhere here, and one goes in this direction. One of the asymptotes goes in the 180-degree angle. One of the asymptotes goes in the 60-degree direction. Let us say in this direction. And the other one goes in the 300-degree direction. Let us say like this. Okay. Now it is important. I think this is wrong, so pole should be here now. Okay. So now we are interested in finding out at what particular angle the root locus departs from this particular complex root, which is given by the angles made by a particular locus point. Let us say this, if this is S0 locus point, we will join all the phasors here and this one also. We are interested to find out this phi p. Okay, and we have different angles. This is our theta 1, this is our theta 2, this is our theta 3. So we have summation of angles of zeros as, also we have this other pole also. So this will be theta 4. So we will be having theta 1 minus summation of all the angles made by poles. So we will be having theta 4 plus theta 3 and theta 3 and theta 2, which will give us phi, and phi p will be equal to, phi p will be equal to 5. Now if this is 60-degree angle, so asymptote is traveling or going at 60 degrees, so the angle of departure here will be around 50 degrees to the horizontal. So phi p will be around, or the phi will be around 50 degrees, so that at infinity this particular segment, or the asymptote and this particular root locus will be. So this is how you calculate the angle of departure from the pole. How to calculate the angle of arrival? So it is given by phi p is equal to 180 minus phi, and again for phi it is nothing but summation of angles from 0 minus summation of angles from poles. Again the calculation is same as we saw in the angle of departure. And what are breakaway points? The breakaway points of root loci are given by dk by ds, which are specifically the points at which the multiple roots occur, as we saw in the example where we had the root loci diagram as follows. So we had 3 zeros and 4 poles, wherein this was on the root locus, and this part where we had a circular shape going towards other poles. If you look closely at this particular point, we have 2 roots, or the multiplicity of roots. These are the roots at which there occur 2 roots, or the multiple roots, and to find out these roots, these are known as, this point P and this point Q are known as breakaway points, which are calculated by dk upon ds is equal to 0. So if you have 1 plus f of s is equal to 0, or say 1 plus k a of s upon b of s is equal to 0, what you will do to find out k is, k will be equal to minus b of s upon a of s, and you will be required to differentiate k with respect to s. and equate it to 0 to get these breakaway points where there are multiple roots. So this was the final rule to draw a root locus. Let us see the session summary. We saw that root locus technique is geometric and qualitative stability analysis is done through this technique. Root locus is the locus of zeros and poles of a transfer function in S-plane as certain parameter is varied, such as a gain k. Magnitude and angle conditions are important for root locus. We also saw the circular shape that occurs after a breakaway point is essentially because we saw that in angle condition there forms an equation where the equation satisfies the circle's equation. We didn't give a proof, but that is the main reason behind that circular shape. And this is how magnitude and angle conditions are very important. Once angle condition is satisfied, you can go forward and check the magnitude condition. But if angle condition does not satisfy, there is no point in checking the magnitude condition. Also, root locus is symmetric and there are certain rules by which you can draw a root locus and analyze the stability of the system. We saw that once the system goes past the j omega axis, system is becoming unstable. Also, the root locus part which lies far on the left hand side of the j omega axis is more stable than the part of the system where system lies near the j omega axis, where it lies on the left. So this is where we will end this particular session. Thank you.